So this week, very happy to introduce Tom Davis. So older members of the department will remember that Tom did his PhD thesis in our department, supervised by Marcel Franz. And then he's gone off to work in finance. So one of the things about certain parts of the finance industry you discover is that there's lots of physicists hired in there. So one of the things students wonder is how they get from being a physics student to having a job like that. So that's exactly what Tom's going to talk to us about today. He's the director of fixed income and derivatives research at this company called FactSet. And he's going to talk about basically the connections between physics and finance. So it's all yours, Tom.
Thanks, Douglas, for the introduction, and thanks, Marcel, for setting this up. It's really an honor to be here virtually giving a colloquium at UBC. I sat through many in my tenure as a grad student there, so it's good to give back to the community. Yeah, I want to talk about the connections of physics and finance and why it's a natural home for physicists to go after a degree. And so what I want to do first is, so why are there so many physicists in finance? I want to ask and answer 4 questions. First, what is finance? To level set with the group on what we're talking about, because people probably have different conceptions of what it is. What kind of problems are there in finance that need to be solved? What type of observables are modeled, and what types of models are used to model the observables? And finally, what type of mathematical tools are required? And we'll do this through the lens of the investment process, and I'll focus in on 2 aspects, one risk and the other derivatives pricing, because that's where most of the physicists are. And specifically, I'll go deep dive into the derivative pricing, because that was my path into finance after physics. So I'm going to start with some potentially surprising facts. These might be known to people, might not. For instance, who was the first physicist to make the crossover into finance? That was Sir Isaac Newton. He had an appointment as the Master of the Royal Mint in 1699. And he took the role quite seriously, as he did with all of his endeavors. And other famous physicists, Bernoulli actually discovered Euler's constant E through looking at compound interest in bank accounts. I'm not going to argue whether this is historically accurate. There's a link if you want to argue with the author of this. Shannon, Kelly, and Thorpe were the crew who went to casinos in Las Vegas and tried to beat the dealer with some success. Stratonovich, you hear, of course, the transformation of physics. He has an alternative derivation or formulation, really, of stochastic calculus. It's more apt for manifolds, more deals with manifolds better than Ito's. And we'll talk about Ito's calculus in this talk. Nigel Goldenfield, UI, Indiana Champaign. He founded a company called Numerics, which I actually worked for 4 years. There's an interesting book about that endeavor called The Wrong Number Faster. Feynman, of course, pops up everywhere. So he has a central role in finance, the Feynman-Kac theorem, and that's going to be something we talk about in this talk as well. Mandelbrot in the late 70s, looking at stock prices, said there's got to be something fractal about this, and did a lot of research that at the time was not really picked up, but has recently come into vogue. Jim Simons of the Chern-Simons quantum field theory runs possibly the most successful hedge fund of all time, Renaissance Technologies. And finally, Luca Capriati's condensed matter physicist, but he brought path integral formalism into quant finance, which actually just had a paper accepted in the journal Derivatives based on the path integral formalism. And on the right, you can see some UBC connections. Just to your question, I don't know those names, but these are the names were in my cohort or took a similar path around the same year as I was in UBC. So this list is probably not exhaustive, and especially it's only really temporally between 2000 and 2006. But that's quite a name, quite a list for that time period. And the last potentially surprising fact was that UBC was a quant finance powerhouse in the late 70s. They had professors that introduced finite difference methods and Monte Carlo methods into finance, which are used extensively to this day. So the next I want to show some research that is going on, current research that's going on in finance. The Journal of Derivatives just had a sort of a crossover issue and had physics techniques in finance just a couple issues ago. So I'm going to put up some research, that's contemporary in finance. And you'll probably see some surprising words here, like supersymmetry, dissipative instantons, path integral approach, things like this. And one thing I will say is, like, not every physics technique is going to be useful and applicable in finance. And so a lot of these might be, people with a PhD coming in and trying to use what they know, like every problem's a nail, right? If you only have a hammer. But the application of physics techniques in finance is probably quite more diverse than you might appreciate outside of the field. And one of the ones I want to point out is the quantum annealing. That's Gilly Rosenberg's research at 1QBit. And I talked to Gilly and the founders of 1QBit, and they said the reason we are thinking about finance as an approach for quantum computing is because if we make a 1% of 1% difference, that means a lot to finance, but maybe in other fields it doesn't mean so much. 1% or 1%, or we call it in finance a BIP. Like if you measure your investment outcomes in BIPs. So percentage of percentage points. So in the upper left corner is Forky, who's a Pixar character. And I have a 2-year-old, and it's one of his favorite characters. And his claim is that he was made from garbage 4 days ago, so he doesn't have a lot of answers. So he has to ask a lot of questions. So he asks, what is art? What is leadership? What is a pet? So I'm going to use Forky to say, what is finance? So fundamentally, finance isn't about fancy mathematics or fundamental theorems. It's about decision making. It's a tool for individuals and companies to make decisions, such as, should we acquire this company? Should we increase our investment in making these widgets? Should we raise funds by issuing debt or equity? How much should I save for retirement? What types of investments should I make, and how often should I make modifications? Did my investment style pay off? And this is the Shannon, Thorpe, Kelly. Can I be clever and increase the chances of a gamble being profitable? Or can I reduce the risk inherent in investing? And Ambrose Bierce has a funny definition of finance: the art or science of managing revenues and resources for the best advantage of the manager. The pronunciation of this word with a long I and the accent on the first syllable is one of America's most precious discoveries and possessions. I guess in Europe they say finance. I'm going to continue with finance. So what kind of problems arise in finance, and why, and how are we going to solve them? So that's the next question. So I'm going to take the view of the investment narrative. So if you're about to make an investment decision, you want to say, what am I going to invest in, and why? Sort of justify that choice. And I put on the upper right a bunch of companies like Fidelity, Vanguard, Neuberger, and Odlum. And these are companies that will do this for you. You go to them and they will take your profile, see your risk tolerance, see if you have any risk aversion or time to retirement. All these factors come into what your portfolio makeup should be. And they hire a lot of people who are equity analysts, who are typically charter members of the CFA Institute. CFA stands for Chartered Financial Analyst, or Certified Financial Analyst. And if you may have noticed that I actually have this designation on the first slide, the title slide. And what it entails is a series of 3 tests taken a year apart. 8-hour tests, 3 8-hour tests, 4 hours in the morning, 4 hours in the afternoon, on a variety of subjects like economics, international accounting standards, fixed income pricing, equity pricing. And ultimately, what they want the charter holders to be able to do is take a look at the balance sheet of a company and say, is this a worthy investment? So is there any accounting fraud going on, for instance, or suspicious accounting? And then ultimately what they want to do is create a portfolio for, say, an endowment fund or an individual in wealth management. So the reason I put all these up is the answer to the first question can be outsourced to a company like this. And in the US, Fidelity and Vanguard and Neuberger run a lot of the retirement accounts, 401ks they're called down there. And Odlum is a Vancouver company. So secondly, once I have the makeup of the portfolio and I've chosen which investments to start to put in, I want to know, what are the risks inherent in this portfolio? Am I overweight in the tech sector? And I don't want to do that because I lost a lot of money in Nortel in 2002. Am I overexposed to interest rates? So if interest rates start to rise, which they probably will because they've got nowhere to go, is that going to adversely affect my portfolio? I need to know how the portfolio reacts to the movements of the different factors that drive their value. So once I know the risk, 3, can I reduce any of the identified risks? So this is where a derivative portfolio or derivative securities come in to hedge away certain risks out of the portfolio. And 4 is, how is my portfolio doing? And you don't want to just say like, well, we beat the index by 5%. That's good, we're happy. You need to understand that if you're an investment manager, professional investment manager, you have a certain investment strategy. Say, I know how to pick stocks within the tech sector very well. So I want to go and apply that to my portfolios. If you look at your portfolio and you beat the index by 5%, but it was all because of foreign exchange changes and not because of the tech sector, you've made a bet outside of your core competence, and you don't want to do that. You need to rejig or change your portfolio so that you're only going to be rewarded on the bets that you take. And then should I rebalance my portfolio? Say I invested in the tech stocks and they did really well, well, they're going to be a disproportionate amount of my portfolio now. So I need to reduce the tech. So how do I rebalance my portfolio? And it comes back to step number one. What investment do I choose to put on my portfolio? So the in-present process, there's different aspects of it, and we'll drill down to see which ones attract the physicists. And so when you choose the investments, that's not really the place where the physicists are drawn to. Equity analysts are typically right out of school. They start looking at the different companies and they follow along with the earnings calls every quarter. And there's another quantitative way, but it's not a very sophisticated mathematical approach, but it's called alpha testing. So alpha in finance is defined as the excess return over the market return. So beating the S&P 500 consistently, that's alpha. So suppose you had an idea for a quantitative strategy. Like I think in the tech sector, when earnings per share are announced and they're below the expectations of everyone in the marketplace, the stock dips, but I think it dips too far and will mean revert up to some level. That could be a strategy you employ. So what you do with alpha testing is go back in time, use historical data and apply that strategy and see if it exists. See if you can get some alpha by doing that. And if it does, you can set that strategy going forward. Now, the one funny thing about finance is that the behavioral aspect, having a successful alpha testing model and you go and do it, will actually remove it from the market. So one thing that, because if everyone knows that that dip is going to happen, there's going to be support. When it goes down, people will buy it. So the more people who know about these effects, the less it'll appear in the marketplace. And that sort of hints at the notion of arbitrage freedom or no free lunch. The joke is if a finance professor is the person who walks by $100 bill on the street and says, I can't pick that up because if it was really there, someone else would have already picked it up. So that's not the area that physicists are drawn to in investment. So quantifying risk is one of them. So we want to know and know what the risks are in our portfolio and quantify it to some level and some statistical levels, like what the 95% confidence interval, what do I stand to lose today? And what happens if the credit crisis happens again tomorrow? What happens to my portfolio if the credit crisis in 2008 happened again, or the 1929 stock crash? And then from there, if you know all these answers to how risk affects your portfolio, you can hedge away some risk. And that's usually with derivative securities. And that is where the concentration of physicists are in the finance industry. And I will talk about, I'll do a deep dive into why that is. And finally, measuring and reporting and rebalancing is not an area that physicists are drawn to. But again, you want to see what effects drove my portfolio and when is the ideal time to make changes. And it's called attribution. And you can do attribution in a number of different ways, but you can think of it as all the market factors. I want to identify which ones were the ones that actually drove the return of my portfolio and see if it aligns with my investment strategy. So we want to forecast the risk. Now, the picture in the bottom right, it shows that there's more than just financial market risk. There's also political risk. If you have a big bank that you think is too big to fail and you're not a nice person, people won't bail you out and they'll let you fail. But in terms of market risk, how do I quantify? Well, as I said, we're going to use a statistical measure. And we'll talk about something called value at risk, which is a very popular measure invented by JP Morgan. And it's trying to summarize all the risks in your portfolio into one single number that you can look at every day and monitor. Am I getting more or less risky in my portfolios? So it's the level of loss at a certain percentage. So alpha would be like 95% VAR, 99% VAR. So the level of loss where a greater loss will only occur alpha percent of the time. So you need a cumulative distribution function. You take the integral up to some level, and that gives you 1 minus alpha. You're looking at the left tail of the distribution. So you need this distribution. So how are you going to get this distribution? Well, you can use historical day-over-day changes. So I look at all the stock prices one day to the next day, and I calculate all the deltas. And I do that for, say, 252 days, and that's the number of business days in a year. Or I do it for 500, 750, et cetera. And I have all these market data daily changes, and I apply them to today's market variables, and I reprice my portfolio on all of them. So that'll give me I find the profit and loss on all the scenarios. That'll give me a distribution. I can do a histogram and say, where is the VAR level? So every day I can find out how my risk is changing. Or I could, if I wanted 750 or even 1,000, that's 4 years, is not really that good a measure statistically. I want like 10,000, but you can't go back 27 years and do this. The markets are just different back then, and some variables didn't exist. Some market factors didn't exist back then. So what you do is you look at the statistical properties, correlations, and covariances of the market factors that drive your portfolio valuation, and you construct a covariance matrix that then you can simulate 10,000 simulations if you want. You have to choose a distribution. That's one way, so that's the VAR. Another is the scenario way. What if the crash happened again, 1929, 1987? All the variables drop, all the stocks drop by a certain amount. How would that affect my portfolio? So this is really looking at like the worst case scenarios. What happens in my portfolio in these worst case scenarios? You can try and hedge against these as well. A chief risk officer will not get fired for not predicting the March 2020 pandemic, because we didn't expect that to happen, obviously. But now that has happened, we put it into our tool of scenarios, or our list of scenarios, to look at our portfolios now that has happened. Other measures of risk do exist, like ETL, extreme tail loss. So given I've gone past my VAR, I've lost more than my VAR, so I'm in that 1% or 5% situation. What is the average loss? What's my expected loss going to be? And that one is superior to VAR because it obeys subadditivity, where the addition, if you add two risk measures of a portfolio, it should only decrease. So it has to be less than or equal. And this is a very famous concept in finance that says diversification can only reduce risk. If I own 10 stocks that are diverse, it's better than owning 10 times one stock, because I have that risk of like the CEO resigning unexpectedly of that one stock. Whereas if I average out, I get rid of all the idiosyncratic risk components. So when I said we do the covariance matrix, and then we have to simulate the 10,000 portfolios, we had to pick a distribution. If we pick normal, we would probably definitely determine our risk, underquote our risk. If you look at this table, I looked at a couple indices, the Japan index, S&P investment grade index, and the Euro banks index, and looked at their 10-day return. And we see sigma events of 4, 5, 6, 7, 8 times happening very regularly. If we characterize everything through a normal distribution lens, we see these tail events happening way more often. You know, people say 2008 and 2000 and 1987 are events that shouldn't happen that close together in the lifetime, given the lifetime of the universe. Well, that's under a normal lens. Finance definitely has a lot of these events. They say they're on about a 4 to 5 year time scale, because that's as long as the person in management to get out of management, and the young person to get there who's never experienced the loss. So to demonstrate this, I took IBM stock since 1992, and I did the day-over-day profit and loss, P&L, or returns, and I plotted the histogram. And the green line is the normal, if it obeyed a normal distribution. And you see it clearly does not obey a normal distribution. And so the orange line is a student T distribution with 5 degrees of freedom, and it has a lot more central tendency. So there's a lot more accumulated around the mean. And also, more importantly, it has the fat tails. So on the semi-log plot, you can see that it crosses over the green line in the tail. So it's going to have a lot more events in the tails than the normal distribution. So that's one way, just choosing student T with D equals 5. But there's other interesting ways to add fat tails to distribution. My favorite is the subordinated process. So there's a picture of a financial clock there, Lincoln penny on the clock. And it's a redefinition of what it means for time to pass in the markets. In exciting times, or when market crashes, everyone starts trading in a flurry and time starts to move faster. And in slow times, like around the week of Thanksgiving, American Thanksgiving, or Christmas, not many trades happen, so time is moving slower. And so if we had a standard Brownian motion, we'll get into this in a bit, and then just subordinated that, like what that means is replace the time variable t with another stochastic process that can speed up or slow down at random intervals, we get a distribution with fat tails. Or we could use the fact that the central limit theorem doesn't only have the Gaussian as its fixed point, it actually has something called Levy flights if the second moment of the distribution is infinite. And so these aren't distributions people normally talk about and use in finance, because without a second moment, how do we quantify or talk about risk? But so a Levy flight is like the blue process right there. It sort of wanders around, then jumps, and wanders around and jumps. So it's a jumpy process. And the length of those jump is unconstrained. But if you constrain the jump and call it a truncated Levy flight, you do start to get finite second moments and finite other moments. And so these are things that people use in finance, and they're very good contenders for the stock price movements. So then, so now we know how to quantify risk. What about the derivative securities? Well, one of the main uses of a derivative security is to gain exposure to an asset class without actually purchasing that asset class. Why would you want to do this? Well, one reason is diversification. It always reduces risk. And sometimes you have investment mandates, like you can only be long. If you can only be long, then you can't reduce your risk in a certain sector by shorting that sector. But you could sell a futures contract, which in a futures contract is a derivative on a stock. And that will give you the profile you want without violating your investment mandate. Or you can use derivative securities to hedge. So you set up a portfolio that removes a certain type of risk from that investment. For example, if you're a stock picker and you can pick stocks really well around the world, you're exposed to foreign exchange fluctuations that you don't necessarily have any core competence around. So you can buy, again, FX forwards, which are derivatives on the FX, to hedge away any foreign exchange risks. You're only going to get the appreciation or depreciation in the local currency. Large banks like Goldman, Citi, Royal Bank of Canada, they will speculate on certain events and use hedging to isolate these bets. So for instance, if I think the 10-year interest rate is going to go down while simultaneously the 5-year go up, that means the curve is so-called inverting and it only happens in bad economic times. I want to make a bet on that, but I don't want to make a bet on all of interest rates rising or going down at the same time. So I can make a derivative security with that property and buy it and sell it in the marketplace. Or the next slide we're going to show is protecting against black swan events. Suppose you're an individual investor or an endowment fund, and one of the things is you don't ever want, or there's a mandate in endowment funds, you can never have a loss of more than 7%. So we'll see in the next slide how to do something like this. Now, black swans are defined as rare but very disastrous outcomes. And of course, under the normal lens, they seem rare, but they could not be actually not that rare in finance. So here's an example of hedging. So this is a synthetic portfolio. I'm buying one stock and one option. And an option is the right but not the obligation to buy or sell a stock at a future point in time. So in this, that future point is 3 months, and I'm going to buy a put, which means I have the right to sell it to you. So this is good when stock prices go down. So if I have a stock that's 100 today, I buy a put at 80. If it goes below 80, I can sell it to you, and we've agreed to this, that you will buy it for 80 in 3 months. So this is like downside protection in stock markets. But of course, it's like insurance, and insurance is going to cost something. So we look at these histograms, and the top left is unhedged. So I just have the stock, and my returns are normally distributed because this is my own Monte Carlo simulation. But there's a 2.3 average return, but with a standard deviation of 10 and a max loss of minus 25%. So if I want to say, I don't want that minus 25% possibility, I'm going to start buying options, put options. So the next middle top is the strike price, is what I can sell it back to you for, is 80. And it doesn't really change the portfolio much because the stock never really gets to that level. I've only reduced the mean return by a couple of basis points from 231 to 229. Standard deviation's not really, only 4 basis points reduction, but the max loss is capped at -20 now. So I've actually shaved off 500 bips or 5% from my max loss. If I go to 90, now it's more likely that this option gets exercised. And you can see it basically like the risk, if you call all the left tail the risk, it's all being stopped at a certain level. And that's the action of this option that we bought. But you can see the mean return is now down to 2.17 from 2.31. It's 20 bips. That's a lot in the financial world. And my max loss is now -10. And I can do this more and more. And you can see a reduction of your mean return and a reduction of the risk. And a maximum loss obviously goes up to some constant. So if you do this, if you bought a very, very high strike put and you held the stock, you're definitely going to exercise the put. And then it turns into a portfolio of no risk. Then you're only going to get the risk-free rate, which is what you could have gotten a bank account, because the two securities or have the same financial economic impact. And we'll quantify that a bit more in a later slide. So now what type of observables are modeled and what type of models do we use? Now, I think I've said a lot of observables already. We talked about stocks, we've talked about interest rates, we've talked about foreign exchange rates, there's commodities, there's option prices, interest rates, there's government yields, provincial yields, bonds, municipal bonds. There's interest rate swaps, which big banks use to swap obligations like fixed rate for floating rate obligations. There's issuer-specific yield curves. So I take all the outstanding bonds of Microsoft, say, and I look at if I get a 20-year bond versus a 30-year bond, what my difference of interest rates is. Volatility is important. And so at the top, we have the S&P 500 index, and that spiked down as the March 2020 COVID pandemic. And you can see at the bottom, the volatility spikes up at the same time. Now, typically, there's this anti-correlation. Almost always, there's an anti-correlation between price levels and vol levels, especially in the S&P. And so the vol level is around 12% always. It goes up to 25% sometimes, but you can see in March of 2020, it went up to 90, which is not quite unprecedented. In the 2008 global crisis, it went up to near those levels, but 90 is very, very high for the volatility index. Some people call it the fear index because of this. If you look at the right, this is how some traders, this is a FactSet screenshots, little promotional plug. This is how traders will come in and look at the market. So they'll have these heat maps and it'll just continue ticking all day with green is up and red is down. And if they can just look at it and see how the market's doing, or if they suddenly this broken into sectors like consumer staples, materials, infrastructures, industrials, healthcare, real estate. If suddenly a whole sector's going red, there's probably a market event that's happened that he has to look into or she has to look into. What other variables do we look at? Correlations. These are the correlations between the S&P 500 and IBM, FactSet, Microsoft, Gilead, Pharmaceuticals, and Goldcorp. Most are positive, but you see Goldcorp is negative, and that's because when the S&P goes down, flight to quality, people start to buy gold, and Goldcorp is a company that produces gold, mines gold, so they're tied to that. Foreign exchange rates, so the bottom left is a triple. It's called a triple if you have a triangle. Canadian to USD, USD to GBP, GBP to Canadian. They all should be related in some way. And that's a triple that's very important to me because I've got retirement accounts in all three currencies. But you can see there's a lot of FX data. That's the right-hand side just shows all these pairs and all the forwards on them. Remember, you can hedge with FX forwards. You need to know how all the forwards are being priced, as well as what we call spot. If you just went and changed cash today, that's the spot versus the forward. And there's credit information in the market that we also observe. So this chart is looking at a credit spread. Credit default swaps I won't talk about. They're like insurance, but don't say that to a regulator or you'll get in trouble. The charts on the bottom are showing two bonds and how they reacted in the March 2020 crisis pandemic. The left-hand side is Microsoft, which did spike up to about 200 bips, which is 2%. and then came back down to normal levels. And the bottom screen is comparing that against how treasuries did at the same time. Treasuries did not spike up because no one thought the pandemic was going to make governments default on their debt. On the right, however, we have Hertz Rent-A-Car, which during the pandemic spiked up, but now we're looking at 8,000. That's like 800% on a bond. Price and yield are inversely related. So that means the price of this Hertz bond was driven down to pennies. And that's because I think that bond defaulted. No one was renting cars, and Hertz just did not fare well through the global pandemic. So now we come to what we call the fundamental theorem of quant finance. Now, there's not many areas in finance that we can hang our hat on in terms of a solid mathematical foundation and draw, definitive conclusions from, but this is one of them. Arbitrage freedom. If two securities have the same financial impact, they must have the same price. Otherwise, I could go long one and short the other, buy one and sell the other at, say, I do it, the ratios that cost me nothing, and I get a profit for certain. That's called an arbitrage, and that's what the finance professor says arbitrage shouldn't exist, because if they did, someone would do that trade and make sure that the prices came back to equilibrium. It's originally named it's a French word for geographic arbitrage, what we'd call now. The price of gold in Amsterdam was different than New York City, so people bought it one place, shipped it, and sold it for a profit, as long as the shipping costs were reasonable. Now it's more thought of in terms of probability. You can't have a portfolio that initially has zero value and at some time has a probability of 1 of being non-zero and a probability of 0 of being 0. So given that we now know what the problems need to be solved, what the observables look like, and what types of models, arbitrage-free models, we use, what kind of mathematical techniques are involved. So the big one is stochastic calculus. And this extends calculus to functions that are everywhere continuous, but nowhere differentiable. And people actually thought up until 1872 that these did not exist. They thought if a function was everywhere continuous, it was only non-differentiable on a finite set of points, a set of measure 0. And I like this quote from Newton, because we're extending calculus into the stock market, which is the madness of a crowd. I can calculate the motions of a heavenly body, but I cannot predict the madness of a crowd. He lost about £7 million in today's currency, investing in a South Sea bubble. So what kind of functions could be so pathological? If you look at, so Weierstrass in 1872 came up with one by looking at basically a Fourier. You take a sine and you start adding on more frequencies in a very specific way. And he was able to show that this is nowhere differentiable. Poincaré and Hermite at the time did not like this. They called it a monster and a lamentable scourge. And it turns out there were mathematical proofs that had implicitly the fact that these functions could not exist. So some proofs were actually upended at the time. But if you look at stock prices, this is almost exactly what you'd expect when looking at stock prices. I have those stocks we looked at before: IBM, FactSet, the S&P, Microsoft, Gilead, and Goldcorp. There, it's a log plot, semi-log plot, but it looks exactly like we're talking about. And one thing that on the Weierstrass picture, you zoom in and you see that it's still, when I zoom in, not continuous. Or sorry, not differentiable. And that has to be, if it's nowhere differentiable, the more and more you zoom in, you always have to see cusps. You can never see a straight line. And if this is the S&P over 4 years, and you can see that this behavior is apparent as well. The more you zoom in, the first is monthly, the second, quarterly, monthly, weekly, daily, you see more and more fluctuations in. So the more you look in, and this is even true if you look intraday, and then now there's high frequency finance, which looks at ticks at like millisecond levels, and it's always at all scales. We see this non-differentiability. So how do we do calculus on such a set of functions or processes? Well, we're going to look at something called the quadratic variation, which is a limiting, it's defined as a limiting process. If you take we're going to say it's going to be a process in time now. You say subsequent times, you take the difference of the function and you square it. And then it's defined as a limit as the space of these go to 0. Now, any function that's differentiable will have zero quadratic variation by the mean value theorem. And quadratic variation only accrues when the process in an area when the process is non-differentiable. So for things that are non-differentiable everywhere, it's going to have a finite quadratic variation. Now, the thing we base all of our stochastic calculus on is the Brownian motion. And it has the following properties: that the increments, W at a further time minus today, the expected value of that is 0, and the variance is the time. So it's a normal variable distributed as n of square root of 0 and square root of time. And by Wiener's theorem, the Brownian motion accrues quadratic variation at t. And you could say, well, Tom, you've already said that because of the properties of the Brownian motion. But he proved that this is true not on average, but on a pathwise basis. So this is very important. So what I've done is for the stocks we've talked about is graph their quadratic variation scaled by their variance. And it's actually quite amazing. They fall so close to a line. But the black is the Brownian motion. And you can see that's just one Brownian motion. There's no averaging going on here. Just the quadratic variation definition is being used. And it's linear. You might say, well, it's wobbling up and down, but that's just because I couldn't get my dt to be infinitesimal. It's based on a computer, so it needs to be something finite. And the one thing I want to come back to is that subordinated process. These things look pretty much linear for a while, and then you can see a big spike up at 2008, and then you can see another big spike up in 2020. Well, these are the crises. So it looks like if we say then that the clock is not the wall clock, but it's the quadratic variation that's being accrued by your stock, you can say that, well, it does spike up. Time goes faster in crises. And I think this is a nice visual way to think about a subordinated process. But anyway, we need a new calculus to deal with these functions that have non-zero quadratic variation. If you take a function and you put in a stochastic process or Brownian motion, the second order differential is going to be proportional to the quadratic variation. And therefore, you cannot ignore the second order term. For instance, d of WW is dt. So this is sort of people say dW squared is dt, and that's where this comes from. That's not true. You're talking about the infinitesimal of the quadratic variation. But nonetheless, you have the second order term that you have to add in the calculus. So there's some intuition here. So take the process dx equals x dw. You might say, well, I know how to do that from first year calculus. And I have the exponential of the Brownian motion, but that's not true. That's sort of a pre-Ito concept. So we have to take into account the fact that this process has Brownian quadratic variation. In a Brownian motion, the probability of an up jump for a given size is the same as the probability of a down jump of that given size. It's normally distributed around 0. So, but if a process has convexity, if a function has convexity, we'll talk about positive convexity, then that corresponding up jump results in a bigger delta up in the function than the corresponding down jump. There's going to be some bias upwards, and we can see that in this black and blue graph. Now, this is analogous or identical to Jensen's inequality, which is probably very familiar to you, that the average of the function of a random variable is greater or equal than the function of the average of the variable with positive convexity. So what's happening in the true process using Ito's lemma solution is the exponential with the -1/2 t, and that's correcting for that upward bias. And you can see in this animation, the black process, which is the naive guess, it does jump up frequently, and then there's no really way to get it back down because it's the same, we're putting in the same Brownian motions for the blue and the black, and so it just gets sort of stuck up, and that on average will result in a drift up that the original process doesn't have. The process dx equals x dw, if you take averages on both sides, it's equal to 0. So the process has to continue at 1 on average indefinitely. Now, some of you might say, well, that's not true. It depends on where you take the limit of the x, and that's a valid point. That's the difference between Ito and Stratonovich. When you take when you define a stochastic integral in Ito sense, the x is taken at the beginning of the interval, whereas Stratonovich is taken in the middle of the interval, and that sort of preserves a lot of the calculus operations, and that's why it's better to be when you embed a Brownian motion on a manifold. But in finance, we use Itos, and for all but very esoteric cases, they turn out to be the same formulas at the end of the day. They just look different at some of the steps. It's like a coordinate transform in general relativity. So let's put this together. We have the no free lunch, arbitrage free fundamental theorem of calculus of quant finance, and we have the extension of calculus to random processes. So let's assume a log normal stock price, ds equals mu at ds SDT plus sigma SDW. That's a stochastic differential equation, SDE. Now you might say, well, Tom, you already told us that log normal process or normal returns is not useful in finance. Well, that is true. For the fat tail distribution, that's more important in forecasting risk, which is a forward-looking thing, than what we're doing here, which is implying what the market is telling us, taking some information from the market. So all we need to do is get a formula from which we can glean information, and it'll be implied volatility in this example. And then we can start modifying the equations to be more realistic in terms of distributions. So I'm going to set up a portfolio, just like I talked about, that's going to have no risk. And I'm going to synthesize a stock option with a portfolio of the option itself and a delta times the shares, so delta number of the shares. I don't know delta at this point, but I do know that at expiry, if I sold that option C, someone can make me buy it back from them. So the delta, if the stock price is above the strike, I better own that option. So I need one share of it at expiry. So we now use Ito's calculus, Ito's lemma, to determine the price of that portfolio, knowing the option depends on the stock price, and we have the SDE of the stock price. That results in this equation. We see that the DW term is the random term we can actually set to 0 by a particular choice of delta. And if you do that, you eliminate the risk, and therefore that portfolio is risk-free and therefore has to accrue interest at the risk-free rate. It has to behave the same thing as putting money in a bank account. Otherwise, there would be an arbitrage. So after rearranging a bit, you get the equation at the top right, and that's the Black-Scholes partial differential equation. And the one thing, if you actually want to do this in practice, which people do, option market makers do this, you need to come in every day or every hour, or however frequently you want, and change the number of shares you own by delta, or else you won't have this perfect hedge. And it's called the portfolio won't be self-financing if you don't do it fast enough. And there's a closed form solution of this formula, which they got the Nobel Prize for, which is in the bottom. And basically, it's the heat equation in reverse. So it's a parabolic elliptical differential equation. I forget, one's with the T term, one's without. And so, we can solve this in probably a third-year PDE course. And this can be generalized, and it was done so by Feynman and Kac. Kac was a Polish mathematician. And this makes this connection between PDEs and finance very strong. So basically, he did this in general, as opposed to just for stocks and options. So whenever you have observable S, could be a stock, could be an interest rate, could be whatever commodity. If you know or posit the stochastic process it follows, then you have a partial differential equation to solve. And so what the theorem states is that the price of the option today is going to be the expected value of the cash flows at maturity discounted back by this e to the minus RT integral RT term. Now you might ask, what is that? Well, that is another important concept in finance. It's called the time value of money. And if I ask you, would you rather $100 today or $100 in a year? You'd probably say today, because you could use it and invest in something and probably get more than $100 in a year, or put it in a bank account or a one-year GIC and definitely get more than $100 in a year. But if I said $100 today or $1,000 in a year, you'd probably say $1,000 in a year. So there is some value of money at which you are indifferent. And that is related to the discount factor. So it turns out that the amount that I would put in a bank and get in a year is that break-even point. And that's why if we want to talk about money in the future, we need to discount it to today's values. So I've gone ahead and solved the Black-Scholes partial differential equation on a grid. I think I used fully implicit in a programming language called Julia, and for 3 different boundary conditions. One is the regular hockey stick Black-Scholes vanilla option. The next is a digital. So this is the contract says, if the stock price is above a certain level, I'm just going to give you money. I'm not going to make you buy the stock. We're just going to agree that I give you $100. It's like a bet. I bet you IBM is going to be above 100 next year. Okay, I'll take that bet. And then the next one is a butterfly spread. It's called in finance, but you probably know it better as a Dirac function. And so that's if that you can't make this bet, but I bet you IBM is going to be exactly 101 in a year. That would be this. There's not a traded contract. The digital is a traded contract, but the Dirac is not. But now, if you look at the PDE, I'm solving with a Dirac boundary condition. That's the Green's function. In finance, you mix in discounting, and it's called the Arrow-Debreu security price. And if you know the Arrow-Debreu security price, you can get any payoff just by the convolution integral. So in derivative pricing, there's three ways you can solve a problem given by this pyramid, because the top of the pyramid's narrow, so there's not many available. It's in closed form. If you happen to know the Green's function exactly, and you have an easy payoff distribution like the maximum function, you can get an exact solution. If you don't, or if the option is path dependent, so it's like suppose you said the option is on the average of the IBM over the next year, as opposed to the time at maturity. So that's a path dependent option. You can't do this integral approach anymore. So there's two other approaches. Backward propagation. This is mostly partial differential equations. You can solve the PDE using techniques that were very well known, like the fully implicit, fully explicit, or Crank-Nicolson approach. There's also something in finance called binomial and trinomial trees, which was thought to be a fully explicit approach, because then in fully explicit, you can get all the weights exactly, and there's no matrix inversions to do on the grid. But I recently published a paper in the Journal of Derivatives that show that it's actually more of a Green's function approach with the path integral formalism of quant finance, as opposed to a fully explicit PDE approach. And finally, if you start having options with many stochastic drivers, so say a basket option. So now my option depends on the basket of Tesla, IBM, Microsoft, and FactSet, some average of that or something like that. So the payoff depends on the average of those stocks at maturity. I have to have a stochastic driver for all of those. So my PDE is now 4 or 5 dimensional, and that gets very computationally expensive. And it's called the curse of dimensionality, and you can solve it by Monte Carlo, which solves the curse of dimensionality, gets around it by the square root of n convergence, regardless of how many drivers you have. And so there's a lot of Monte Carlo techniques used in finance as well. Kind of, it's like going to the back to the Feynman-Kac theorem and saying, now, okay, I'm going to discretize and solve that stochastic differential equation using some approximate techniques and just do that expectation, as opposed to transforming it to a PDE and solving it, which the other two approaches, backwards propagation and closed form, do. So 47 minutes, good timing. We get to our conclusion. So I hope I have conveyed a little bit of why is finance a natural fit for physicists. The skills that you learn in the courses, statistics, analysis, differential equations, and programming, are all required skills in like the risk and the derivative pricing areas. Obviously, physicists are excellent problem solvers. People have a natural curiosity, I think, to get into physics in the first place. And so when they just get into finance, it's a new set of problems that are very interesting for them to solve. When I first transitioned into finance, I was worried it was going to be a boring application of the mathematics, but I was happily surprised that it's very deep. Stochastic calculus is a very rich subject that's still ongoing in terms of research. And on broad levels, the problem-solving process is the same. You need to come up with a problem to solve, be able to write it down mathematically, and solve it with the tools you have, learn new tools, or create new tools to solve those problems. When you're just a junior quant, the problems that you come up to solve are given to you, and they're usually just fix this algorithm. But once you are in the field for a while and you get to lead a research group, you have more time to sit down and think creatively about what problems are interesting to solve. And the last point, I won't make it too strongly, but it is probably easier to teach finance to a physicist than the math to an econ major. And there are very well-known exceptions to this, like Peter Carr is one of the most preeminent quants today, and he did an econ and finance background. So at that, I will leave up the slide for resources for anyone who's interested. The beginner books are a good level for anyone with an undergrad in physics. Intermediate and advanced, you should probably do after the beginner. There's a couple of books that I think are not on math, but are very interesting. And then 2 links. One is from a Caltech person talking about his path to finance, and one is Nigel Goldenfield, who always gets asked the question, how do I prepare for a job or an interview in finance? So he finally put up a website so he didn't have to repeat himself all the time. But at that, I thank you for your attention, and I hope I conveyed some interesting information here, and I do have time for questions.
Great, thanks, Tom.